all that was a secret for your ears only, I guess. And whoever is on here. Me 3 times. But I'm only 2 of those. All right. Change this right away so I don't forget. All right, we're recording. We're off to the races. Got my calculator. Man, oh man. Yesterday was such a weird day for me. Turns out I'm taking on another course, so I'm a little bit like, what? What's happening? But anyways, you guys are all good. Let's do some calculus. Or at least kind of pre-calc still, right? All of chapter 1 is basically pre-calc, just kind of reviewing everything that you definitely need to know heading into the actual course. So on WebAssign, right, you've got a diagnostic test and assignment 1. The diagnostic test is due on Friday, so it closes on Friday. And all those WebAssign assignments, I'm not going to open them back up. So just do them before they're due. Yeah, assignment 1 is due on Sunday. So the diagnostic test is due Friday, January 17th. Usually I'm kind of hesitant to say Friday, January 17th, because I usually screw up one of those and it makes it really confusing, but I'm pretty sure Friday is the 17th at 11:59 p.m. And assignment 1 is due Sunday, January 19th, also at 11:59. So I make all my online assignments due at midnight. Why not? Don't leave it until midnight, especially this assignment. So because a lot of people have done these questions, it tells me an estimate of how long it takes people to do it. It is estimating 3.5 hours. So it is a big assignment. Should probably start on it, right? You're definitely able to start it, save your work, come back to it, right? You don't have to sit down and do it all in one go. But so definitely give yourself a little bit of time to work through it. Okay. And so this is on chapter 1. Which will be really close to finishing today, hopefully, but not quite finishing today, just with inverse functions, specifically trig, inverse trig, but well, there's nothing to it. All right, quick review. We developed that catalog of functions, right? So some common functions that we kind of need to have and need to be able to recognize and see if we've got, especially if we've collected data and we're looking at it, then it's good to know, well, I could model this with this type of relationship, right? And so we developed a catalog of function. So developed a catalog, oh my goodness, a catalog of functions I don't know if you guys remember, but I had that moment in the middle of class where I was like, I forgot to talk about something, but I can't remember what. I want you to add the absolute value function to your catalog of functions. And so to that catalog of functions, I want you to add the absolute value absolute value function which you probably know or definitely know, right? The absolute value of x, well, if x is negative, right, we just drop the negative. But what does that look like in terms of the actual function? Well, the actual function, and remember the absolute value is just denoted by 2 vertical bars around. And so the absolute value function is a piecewise defined function, right? And so it can take on 2 different things depending on the value of x. So it's going to be positive x if, of course, x is greater than or equal to 0. So if x is positive, then the absolute value of x is just itself, right? Positive. If x is negative, then the absolute value of x is negative x, right? And this is if x is less than 0, right? Because if x is negative 3, x is less than 0. So then the absolute value of x is negative 3, right? And so that's what the function itself looks like. We understand how to use it and everything like that, but we'll just specify here that the absolute value function, is a piecewise defined function. Piecewise defined function that looks like, you probably remember that it looks like a V. On the XY plane, we've got this V going on. So not much in the way of review, essentially just adding this function here. But the review would just be us going through the catalog of functions again, and let's not do that. So we'll move on. Do a little squiggly thing to show that it's the end of the review. So today, we're going to make use of increasing and decreasing functions. So first thing I want to talk about is just, I forgot we didn't finish. Can I delete my squiggly line? Keep going with our review. Just a little bit. Remember, function composition, should probably mention that, especially because we didn't quite finish the example. Good thing I wrote myself a note. All right. So we also talked about function composition, right? We talked about function algebra and function composition. I'm going to focus more on the composition part, right? F composed with G, for example, where we use G inside of F and then evaluate the function. So function composition, right, such as F composed with G, right? So when you see that F and then a little open circle G, right, you read that as F composed with G of X, right? Or usually how I just end up reading it, because it does have a nice little O, right? F of G of X, right? Because it ends up being F of G of X, right? So usually I forget to say the F composed with G, right? I just read it as F of G of X, because that's what it ends up being anyways. Right. And we also established that F composed with G of X does not equal G composed with F of X. So plugging G into F is not the same as plugging F into G, right? And that kind of makes sense. Unless they're the same function, right? So there are situations where it's going to work, but more likely than not, they're not going to equal each other. So in our example that we didn't quite finish, example 7 continued, we had f of x is root x, and g of x is the root of 2 minus x. And we were working through some of these. We did f of g of x, we did g of f of x, we did f of x, and then we were working on g of x, which we can rewrite as g of x. G is root 2 minus x. So we want to find g of root 2 minus x. So wherever we see an x in g, we're going to plug in root 2 minus x. And so we get root 2 minus root 2 minus x. We're not going to simplify that. In fact, I don't really see anything that we can simplify, because we can't split that square root because we're minusing or we're subtracting in the middle there, right? So that would be illegal math. We can only split up the square root if we're multiplying or dividing, right? And so, but now, what we didn't do was find the domain of this thing, right? And so what possible values of x can we handle? And so first we said, okay, well, the original domain of g, right, the one that's going into the function, has to be satisfied. But then also the outside function has to be satisfied as well, right? And so we get, so for the domain, we need to satisfy the domain of g of x. And I'll just specify, because it's the inside function, right? Is it okay if I call them the inside and the outside function, right? So the inside function, tricky because they're the same function, right? But here we're talking about the inside function has to be satisfied, right? And also, so we need to satisfy the domain of g of x as well as the domain of g of x. So the domain of g of x, right, the inside function, says that, okay, well, the inside function was the square root of 2 minus x. Because we've got that square root in there, we can't take the square root of a negative number, right? So we have to make sure that 2 minus x is greater than or equal to 0, right? And so we need 2 minus x greater than or equal to 0. Moving things around, right? We get, well, we can do it the slow way, or we can move the x over, doesn't matter. 2 is greater than or equal to x, right? So I always like to have whatever I'm solving for on the left-hand side. So usually kind of closer to the end, I'll do a little switcheroo, right? But we can switch around the equal sign, that's safe, right? They'll still be equal to each other. It's just kind of, I guess, a personal hang up. I like to have whatever I'm solving for on the left-hand side. whenever I can. So x is less than or equal to 2. The slow way would have been to move the 2 over, right, and have negative x is greater than or equal to negative 2. But then you have to get that negative off the x, which is going to be what switches your sign over. And so either way, you're going to end up with x is less than or equal to 2. So that's the domain of g of x. So now we want to talk about the domain of g of x. Well, g of x, we just figured out, is the square root of 2 minus root 2 minus x. Okay, a little bit bigger of a beast, right? Because now we need 2 minus root 2 minus x to be greater than or equal to 0. Right? Because we still can't take the square root of a negative number. And so here we need 2 minus root 2 minus x to be greater than or equal to 0. No matter how you slice it and dice it. Let's do the slow way. Negative root 2 minus x, it has to be greater than or equal to negative 2, right? Moving that 2 over. And then in the switcheroo, right, we get root 2 minus x is less than or equal to positive 2, right? Because we've moved that negative over, multiplied both sides by negative 1, or divided both sides by negative 1, doesn't matter, it switches it over. To get rid of the square root, right, we square both sides, and so we get 2 minus x is less than or equal to 2 squared. So 2 minus x is less than or equal to 4. Now we're back to a similar situation that we had earlier. And so we can do, sure, negative x is less than or equal to 4 minus 2. So x is greater than or equal to negative 2. Unless I went too fast there, right? 4 minus 2 is 2, moving that negative over. Negative 2 switches the sign. Bada bing, bada boom. So now we've got restrictions on x from both sides, right? The domain of g of x and the domain of g of x, right? And so the domain of g of x says, well, x has to be less than or equal to 2. Fine. But then the domain of g of x says, well, x also has to be greater than or equal to negative 2, right? So now we're restricted to be between negative 2 and positive 2, right? And so that's our new domain of this composed function. So our domain, I'll just use a D with a colon, mostly because I've got this page break here, so I don't want them split up over pages. X must be between negative 2 and positive 2, or in interval notation, negative 2 to positive 2, inclusive, right, with the square brackets. So there was actually, oh, any questions about that one? Cool. So there's actually one other example from the function composition that I wanted to do. This is part of the review, maybe not. Where do I put my squiggly line? Here. Good a place as any. And I'm committed to that one. So, well, I should have I reserve the right to change my squiggly lines at any point. End of review. All right. So I also wanted to just go through example 9. And the reason I really want to do this one is because we're going to need the reverse skill of function composition, right? And so be able to recognize smaller functions inside bigger functions, right? And so that's going to be a really useful skill. So if we're given something like capital F of x is cos squared of x plus 9, we want to find functions f, g, and h such that capital F is f composed with g composed with h. Right. Oh, turn my h into a triangle of some sort. Okay. So we want to have 3 functions, and we can nest as many functions as we want. Right? So that's all right. But now we have to decompose this original function into 3 other functions that have been kind of nested inside each other. Okay. The first one that I see, right, is that x plus 9. Right? If we deal with just cos squared around x plus 9, that only gives us 2 different functions, right? But we wanted 3 functions, so we want to break this apart even more, right? And so the key thing to remember is that we could rewrite cos squared as the cos of x plus 9 all squared, right? That square, we can bring it onto the cos, and that's safe. And so we can rewrite capital F of x equal to cos squared of x plus 9 as cos of x plus 9, and just to emphasize, I'll just do all squared in brackets. Because now, right, now 3 things have happened, right? We've got our x plus 9, so that's one of the functions. X plus 9 was plugged into cos of x, right? And then that cos of x plus 9 was plugged into x squared, right? And so, so if we want f of x equal to f composed with g composed with h of x, well, that's the same as writing, if we just kind of nest these with the brackets that we kind of like a little bit better, f of g of h of x. Make sure my brackets all add up. So what that means is that h of x is our very core function, right? That x plus 9 that we were plugging into cos of x. And so h of x is x plus 9. We could have even done 4 functions if we wanted to, right? I of x would be x. H of x would be x plus 9. Right? Just plug in x into x plus 9. It doesn't really do anything, but we could have if we had to. Right? G of x is not going to be the cos of x plus 9. It's just going to be the cos of x. Remember, our x plus 9 is replacing wherever we see an x, right? And so here we get g of x is the cos of x. And then same idea, f of x is going to be x squared. Because we built the rest of them, and then we replace x with our cos of x plus 9 in our square. Nice. Cool. So that, I would say, is going to be a really useful function, or just kind of a useful skill for things like when we do U substitutions, right? So being able to say, well, I don't know how to deal with this big thing, but I know if I replace this temporarily with a U, just any letter, right? And then I'll plug it in later and deal with it later, right? So just things like that. Okay. Any questions about, well, anything? Function compositions mainly? Oh. You guys are just glad you made it. Or maybe not. I don't know. I'm glad you made it. So, all right. Now we get to talk about increasing and decreasing. I think what we'll find, a lot of the stuff in calculus is just kind of like, well, yeah, you hate to say duh, but it's just kind of obvious, but all these things have to be stated. So a function that's increasing just means that it's on the up and up, right? So if this value of x is less than this value of x, then this output is less than the next output, right? If you have a decreasing function, it means that you're on the downward slope, right? And so then we can relate that to how our x's relate, right? A smaller value of x is going to yield a higher value output, right, f of x, and a larger value of x is going to give a smaller output, f of x. So a function f is called increasing on an interval I if f of x1 is less than f of x2, right? The output at x1 is less than the output at x2 whenever x1 is less than x2 on that interval, or in I. It is called decreasing on I if f of x1 is greater than f of x2 whenever x1 is less than x2, again, in I. It's a definition, so I'll put a little block around it, but it is also pretty common sense, right? Because if I drew something, and I'm going to try to keep it on the same page here. If I drew something like x squared, let's pretend. Yes, I'm reached. Well, if I just asked you, hey, on this interval here, is it increasing or decreasing? Decreasing. On this interval here, is it increasing or decreasing? You got it, right? And so, but we have to have this mathematical notation that says, well, if this x is less than this x, then if it's increasing, then this output is less than this output, right? And if it's decreasing, if this x is less than this x, then this output must be larger than this output, right? And so all these kind of obvious things we have to communicate with less obvious mathematical notation, right? And so sometimes it's just a matter of sitting down and saying, well, actually, that's pretty obvious. Right? And so on this interval, right, it's increasing. And on this interval, it's decreasing. maybe I'll put circles around it so it's there. Now we've got a beautiful, what leaf am I thinking of? A lotus? No, maybe not. Maybe like a lily. Anyways, doesn't matter. It's a beautiful flower. Okay. All right. Now that we've established increasing, decreasing, we'll be able to use those facts later on, right? And say that, oh, well, because this thing is increasing, right? It'll have an inverse because it's 1-to-1, and we'll get there. Any questions? So section 1.4 is on exponential functions. Which we will see a lot of. Hey, I forgot an L. Pretend it just didn't draw. If you notice that I forget words, or it's just because I'll say them in my head but not on the paper, yeah, just let me know. Sometimes I'll read my notes and there's obviously a word missing. Like, well, no one caught it, so oh well. So exponential functions, just as a little reminder, right? That's what this chapter is all about, just kind of gentle reminders. So an exponential function has the form f of x equal to 2 to the power of x, for example, right? It's when the x is in the power. Okay. So when the variable is in the exponent, we have an exponential function, whereas the difference is the power function is if we have f of x equal to x squared, for example. Right? Power function is when the variable is in the base. Variable is in the base. So in general, an exponential function is going to look like f of x equals b to the power of x. So an exponential function. An exponential function has the form f of x equals b to the power of x, where the base b is a positive constant. Just do a quick run through of the rules, right, for exponential functions. And so the rules, the first one, you'll definitely know, if x is equal to n, right, a positive integer, hey, you guys are page flip buddies. Nice. Not sure what that means, but You're probably best friends forever. Yeah. So b to the power of n, right, just means that you have b times b times b times b times b n times, right? That much we are probably comfortable, hopefully comfortable with. So we've got b times b times b, blah, 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 n factors, right? Or n times. The second rule, hey, what happened there? A message? Uh-oh. Hopefully I'm not on mute. Hey, you put a less than sign instead of, let me have a look. That is because x1 is still, so for the decreasing, was that the note? Yeah. It's okay because x1 is still going to be less than x2, but the output of x1 is going to be higher than x2. It's hard because you can't see my hands. Anyways, it is okay. Thank you, though. But like you noticed, oh, okay, sorry. Hey, it's myself. Someone must have used my name. But like you see, like I don't really see them. They catch my eye, but then, so if you see a message like that, then please let me know. So I can stay on top of it. So if x is equal to 0, b to the power of 0 is 1. Anything to the power of 0 is going to be 1, except for 0, but we're not going to get picky like that. Right, so just as a rule, anything to the power of 0 is 1. And then if x is negative n, right, so n is still a positive integer, but we're taking the negative of it. N is a positive integer. Then b to the negative n, we can rewrite as 1 over b to the power of n. Right. Usually, I use it the reverse way, right? If I want to bring something from the denominator up to the numerator and kind of have it on the same playing field, right? Then I just negate the power, right? And I can bring it up. To combine like terms, for example, right? And just kind of smush things together. Our fourth rule is that if x is a rational number, something like x equals p over q, where p and q are integers, and of course, well, maybe not of course, q can't be 0, but we're also going to force q to be greater than 0. Then, no dots. Then we can manipulate it quite a few ways, right? B to the power of x, replacing x with p over q, we get b to the power of p over q, which we could rewrite as the qth root of b to the power of p. Splitting up that p over q, we get b to the power of 1 over q, right? Which is the qth root, right? That's our shortcut for taking any root, is just taking it to the power of 1 over whatever root we want, right? And so the 1 over q becomes the root, qth root, and then you still have b to the power of p, which is going to go inside. Or if you wanted to manipulate it even more, you could rewrite it as the qth root of b all to the power of p. Those are actually all going to be the same. So just kind of being comfortable moving around all those manipulations, right, is going to be really helpful. So those are the rules of the game. Any questions before we talk more about exponential functions? No, more exponential functions. Hey, you got it, you got it. All right. I was going to put a box around the rules, but yeah, you know what? I said it, so I will. Why not? These are pretty important rules. Actually, they're really important rules to follow. Whoop. Big box. I feel like we touched on it briefly in our catalog of functions, right? But there's actually 3 different types of exponential functions, right? If the base is less than 1, right? If the base, then we've got this decreasing function. If the base is greater than 1, then we've got an increasing function. And if the base is just 1, it's just this constant. And so there are 3 kinds of exponential functions. Exponential functions, y equals b to the x. Remember y and f of x? We use those pretty well interchangeably. I would treat them as the same thing, right? So if you prefer to just use y, then that's fine, right? Sometimes if we're plugging things into f of x, like function composition, for example, right, then maybe using f of x is easier. But as long as you kind of, in your mind, have f of x and y can be used interchangeably, that's going to make your life a lot easier. Right? And so the exponential function, y equals b to the power of x, well, our first option looks a little something like this. Passing through 0, 1. And this is when y equals b to the x if b is between 0 and 1. Right, we said we had to have a positive base, right? But if the base is between 0 and 1, right, or less than 1, then we've got this decreasing function. Whereas, I'll put all 3 on here. If we just have y equals 1 to the power of x, doesn't matter how many times you multiply 1 by 1 by 1 by 1 by blah, 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 right? It's just going to be 1. And so we've got this constant function, this straight line, passing through 0, 1. Kind of a special case exponential function. And then finally, something like this also passes through 0, 1. And this is if y equals b to the x, as long as b is greater than 1. Notice that all of these functions pass through 0, 1. And so that's going to be just the rule of exponential functions, is that they will pass through 0, 1. So all exponential functions. All exponential functions pass through 0, 1. Since b to the power of 0, right? The exponential function is b to the power of x, but as a rule, right, if x is 0, anything to the power of 0 is 1. As long as b is not equal to 0, right? But even in our restrictions here, the base can never be 0, right? It's either between 0 and 1, but not inclusive, right? Or 1 or greater than 1. Right? So, nice. Let's just talk about the laws of exponents. A lot of rules and laws and not that fun stuff, but that's okay. So the laws of exponents says that if a and b are positive numbers, and x and y are any real numbers, then, and maybe I'll scoot this down so they're all on the same page. Oops. Then the first law says that, well, b to the power of x plus y, you can rewrite as b to the x times b to the y. And usually how we use this is in reverse, right? If we've got the same base, then we can combine that base by adding the exponents, right? And so we know that, and we probably use it pretty fluently already. Same idea, if you have b to the power of x minus y, well, over b to the power of y, make that a nicer y. I don't know if it worked. So assuming that you have the same base, right, you can combine them by either adding or subtracting the exponents. Why is that? B to the power of y is in the denominator, right? To bring that up top, right, we had that rule that said, well, to bring it up top, I can just say, well, I'm going to multiply b to the power of x by b to the power of negative y, right? Bring it up. And then it's just rule number 1 where I'm adding them up, but I'm adding it with a negative. So then I have x minus y. The third rule says that if you have b to the power of x to the power of y, then we can combine these and say, well, that's the same as b to the power of x times y. Right? Only if you're multiplying. Or only if you're taking the power of a power, I guess, I should say. And the fourth rule is that if you have a times b to the power of x, well, that's the same as a to the power of x times b to the power of x. Right. Okay. So let's do a quick example. We're going to come back to Half-Life examples and problems. So this is kind of just the start of it. Right? And again, you've probably seen it before, but let's do a little run through. So the half-life of strontium 90, I have no idea what that is, but I guess it's written like this, 90 to the top SR. I'm just stealing this from the textbook. Doesn't matter what it is, it's a half-life question, so it can be the half-life of anything, but what the half-life means is that if you've started with some amount, then in the half-life time, it'll decrease to half of what was there originally, right? Or half of what it started with. So is 25 years for strontium 90. This means that half of any given amount or any given quantity of strontium 90 SR will disintegrate in 25 years. If a sample of 90 SR has a mass of 24 milligrams, find an expression for the mass, for the mass m of t that remains after t years. That remains after t years. I'm going to give you guys a little minute to work on it because I want you to have a go. Okay. So how we would tackle this, or might tackle this, there are lots of ways. Well, not lots, but there's a couple of ways. I would say that, well, I know the mass at time 0, right? The initial mass is going to be 24. Yeah. we're also told that, well, the half-life is 25 years. So I also know that after 25 years, I'm at half of 24. Right? And so in order to develop some sort of equation or an expression, right, I'm actually going to keep that 24 in there and use that as a reference point, right, because that's my initial concentration or mass. So after 25 years, we're at half of 24. So 1/2 times 24. So I don't quite see a pattern yet. That's okay, right? But we also know that the half-life behaves the same way for the next 25 years, right? So after 25 more years, right, I'm at half of 24, right? And so after 50 years, right, so another 25, I'm at 1/2 times 1/2 times 24. This is going to be one of those instances where I write my equals across, only because I want to have them kind of cascading down, following each other. And so this is the same as 1/2 to the power of 2 times 24. Notice for the mass at 25 years, right, this is essentially 1 to the power of, or 1/2 to the 1, right? And that 1 is 1 half-life. So 1 half-life. And then here we have 2 half-lives. Right. So that's where that 2 comes from. Time is still in years, right? And so we have to keep track of that. And so we want to look for patterns. The mass after 75 years, right? That's 3 half-lives is 1/2 of 1/2 of 1/2 of 24. 1/2 to the 3. And same thing, that's 3 half-lives. Another 25 puts us at 100 years. And so now we're at 1/2 of 1/2 of 1/2 of 1/2 of 24. 1/2 to the 4 times 24. So 4 half-lives. And this is just going to keep going and going and going. But we can summarize it as m of t. And the tricky part is going to be summarizing the behavior of that 1/2 to the power of however many half-lives we have, right? But if I want to convert 100 into 4, right, I would take t, 100, divided by 25, right? And so you want to find a connection between the value that we're using for t, right, and the 4, which is clearly going to be the power, right? And so what we have is going to be 1/2 to the power of t divided by 25 times 24. I wouldn't say that's obvious, right? But that is something, so a skill that we do want to be working on, right, is being able to recognize these patterns and then being able to say, well, so if this is changing, then this is changing, right? And noticing the connection between the number of half-lives that you've done and t. So, and we can manipulate this a lot of different ways, right? We've got 2 to the power of t over 25 in the denominator. And so we could bring that up, for instance. 24 times 2 to the negative t over 25. There's lots of different ways, right? And so as long as we're comfortable working with these exponents and we're comfortable working with the laws of exponents, we can manipulate this any way we want, right? We can keep going, right? Or 24 times 2 to the negative 1 over 25, all to the power of t. All of these are saying the same thing, right? So depending on how you want to display your function, you'll have to manipulate it. Using any one of these, part B, if we want to find the mass remaining after 40 years, right? So 40 wasn't one of these half-life instances, right? But now using this m of t formula or function, we can find how much mass would be remaining after t equals 40 years. And so now find the mass remaining. Find the mass remaining after 40 years. Correct to the nearest milligram. So like I said, we can use any of these m of t functions. I'm just going to use the first one. I think it's nice. So m of 40 is 1 over 2 to the power of 40 over 25 times 24. Good thing I brought my calculator. 40 over 25. 1 over 2 to the power of 1.6 times 24. 2 to the power of 1.6. And 1 over that times 24. As soon as we get a decimal approximation, right, I'm going to use the squiggly equals. So as soon as I'm getting rid of exact answers, I want you to get in the habit of using the squiggly equals just to remind yourself that, hey, this is an approximation, right? And so if you're using approximations later in your work, right, you're going to get further and further from the true exact answer. But that's often that's okay. But just so you know. So it's approximately 7.917047465 milligrams. To the nearest milligram, I would say that's 8 milligrams, approximately. Nice. Maybe I should start doing my examples in a different color so you see when they've ended. Feels like a lot of things to keep track of, but I'm also pretty confident I can do it. So I'll try to do that next time. For now, that's the end of our example. How about? I don't know. A work in progress. All right. Have you guys taken calculus maybe in high school or, yeah? So you guys know that tangent lines are coming. Oh, limits. Oh, mama. You like limits? Okay, go see this girl. No, that's good. No, so that's where we're headed. And so we're going to be talking about tangent lines. Tangent lines, right, are the lines that touch a point, and only one point, just briefly on a curve, right? And so, and we're going to get into limits and all these types of things just to build ourselves up to be able to find the derivative, right? And so the derivative is just the slope of a tangent line, womp womp, right? And so, but anyways, so all of this is kind of building up to that. Oh yeah, in case you didn't know, Calc 1 is derivatives, Calc 2 is integrals, which are basically the opposites, right? Yeah, sort of, but it's the area under the curve instead. So, so Calc 1, derivatives, slope of the tangent line. Calc 2, integrals, area under the curve. That's it. No. And then Calc 3 and 4, you do the same thing over again, but with more variables than just x. Right? X, Y, Z, P, Q, R. Nah, it's plenty. So anyways, some formulas are going to be greatly simplified if we pick a base so that the slope of the tangent line at 0, 1, remember 0, 1 for our exponential functions is like that special point that all these exponential functions are passing through. And so if we pick a base where the slope of the tangent line at that point is 1, right, things are going to be a lot easier to deal with. And so QE, the number E. Anyways, so some formulas will be greatly simplified if we choose the base B of y equals b to the power of x, so that the slope of the tangent line at 0, 1 is exactly 1. That number is E. And you've probably got a e to the x or an e on your calculator, depending on how sophisticated things are. But most calculators have an e or e to the x button, right? And if you just want e, well, that's e to the power of 1, right? So you can use that on your calculator. But e is one of those irrational numbers, just like pi, right? But an approximation would be 2.71828. Oh, I skipped a 7. 2.71828. Pretty sure there's a song. My supervisor used to hum the song 2.71828. And it can keep going, but anyways, I've yet to look it up. I'm never that curious, I guess. Or to more decimal places, 718281828. 28, blah, 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 blah. But anyways, that's plenty, right? It's roughly 2.7, right? So how we can get there is we can use bases of 2 and 3 and just kind of narrow it down, right? But then eventually we land on this number E. Okay. We call f of x equals e to the power of x, which is actually the function that I told you to use on your calculator. Right? This one's a little bit weird. It's just got an e and then you have to raise it to the power of whatever you want, which I guess makes a little bit of sense. But most calculators that I've seen have an e to the power of x button. So we call f of x is e to the power of x the natural exponential function. The natural exponential function. I guess I should have tried to squeeze that onto the same page. Please stay on the line. Because we're starting a new section here. There. Squish it all onto one page. Okay. So that's all we're talking about, the natural exponential function, but don't you worry, it will be coming back. So for now, it's the special case with special b where the slope of the tangent line at 0, 1 is going to be 1. Right? And that's all we need to know for now. Any questions before we start talking about inverses? Logs? No. No. Can we just not talk about inverses and logs? I wish we could. I wish. So 1.5 is inverse functions and logarithms. You got it. Uh-huh. You're in luck. Okay. So this is the last section that we're going to talk about in chapter 1. And so we just need to talk about inverse functions and definitely logs. Logs are just the inverse functions of exponential functions, right? So if you want to bring something down from the power, right, then so if you have an x that you're trying to solve for, the only way to bring it down, right, would be to apply a log to it. And we'll look at the log laws that actually bring it down. But for now, we'll just talk about one-to-one. So only functions that are one-to-one have an inverse. So only functions that are one-to-one have inverses. Oops. What does it mean to be one-to-one, you ask? Well, just means that one output can't map back to inputs, and one input can't map. No, it can't map to the same output as another input. Anyways, let's let the definition do the work. But anyways, it just means if you're drawing it, right, they're just going one-to-one. So a function f is called a one-to-one function. A one-to-one function if it never takes on the same value twice. the same value twice. That is f of x does not equal f of x, or f of x1 does not equal f of x2. That makes more sense. Whenever x1 is not equal to x2, right? If x1 is equal to x2, then yeah, you expect them to have the same output. But if your inputs are different, you expect your outputs to be different. So whenever x1 does not equal x2. We can check if a function is one-to-one graphically, right, by using the horizontal line test. So we can check if a function is one-to-one graphically by using the horizontal line test. Which says that a function is one-to-one if and only if. Have we used IFF, if and only if? A couple of times? Cool. Can't remember. If and only if no horizontal line intersects its graph more than once. Its graph more than once. So if, for example, we have something that looks like right. If I draw a horizontal line here, then I'm intersecting it twice, right? Making this function not one-to-one. And the consequence of that is that it's not invertible, right? We wouldn't be able to find the inverse of this function. Right? Therefore, not invertible. Whereas if you have, and the easiest example is something like an increasing or a decreasing function, right? Where we've got something like this. Well, at any point, I can draw a horizontal line here, and it'll only intersect the graph once. So this is one-to-one. Therefore, it is invertible. Okay. So let's just talk about the definition of the inverse, right? It assumes that you have a one-to-one function, and that's our hang up with the one-to-one is, okay, well, it has to be one-to-one in order to be able to find the inverse. Right? And so let f be a one-to-one function with domain capital A and range capital B. Oops. Then its inverse function, which we show f to the power of -1, right? And we read it as f inverse. Right? Then the inverse has domain B, has domain capital B, and range capital A, and is defined by f inverse of y is x, and f of x equals y for any y and b. Capital B. Put a square around this. So if you take the inverse of y, then you end up at x. And like we said, f of x, we can replace it with y. One thing that I do want you to note, right, is that the inverse notation doesn't mean that it's 1 over f of x, right? So I'll just make a note here. Note that f inverse of x is not the same as f of x to the -1, because that would be 1 over f of x, and that's not necessarily true. If you have found the inverse of a function and you want to check to make sure that it actually is the inverse, right, then we can use function composition, right? We're going to cut out the composition part, but just notice that if we say as a rule, f inverse of f of x equals x, well, if I had to rewrite this as function composition, which we don't have to, but just so you see, right, this would be the same as saying that f inverse composed with f of x, right, plug f of x into the inverse of f of x. And I'll just say for every x in A. And also the reverse is true, right? If I plug in the inverse into f, then I should get x back, right? So either composition and both compositions should just spit out x. So f of the inverse of f of x should also give you x. And so this is the same as f composed with f inverse of x. And I guess I should finish it with equals x on both. Yeah. So if you prefer function composition, then that's great, right? Or if you just like them nested, like in the original, then that's fine too, right? But this is for
every x in B.
So this is how you check if you actually found the right inverse, right? Because at the end of the day, if you compose the two, right, either direction, you should end up with x. Another thing, kind of a neat thing that was established in here that kind of got lost was, okay, well, if f has a domain A and a range B, right, then the inverse has the opposite domain and range. Right? You can use this because it's often easier to find the domain than it is the range, right? Not necessarily, but often. So what you can do is you could find the domain of f, and then if it's one-to-one, you could find the inverse, find the domain of the inverse, and now you know the domain and range of both, right? Because they'll swap sides. So it's kind of handy. Yeah. So, any questions? No. Then let's talk about finding the inverse. So to find the inverse, of a function f, the first step is going to be to write y equals f of x, right? Replace, if you're using f of x, just replace it with a y, because we're going to be working with x's and y's and manipulating them. And so the second step, the textbook says, okay, well, now you can just solve this equation for x, right? So now you've got x in terms of y. Or I know that some other methods say, well, swap the x's and y's and then solve for y again, right? Either way, you're going to end up with the inverse, right? X in terms of y, or y in terms of x. So I'll put both on here, so you have them. So solve this equation. For x in terms of y, if possible, I'll put it in a different, or do you guys remember which ones you did? Did you solve for x and have x in terms of y, or did you swap your x's and y's and solve for y again? Remember? Open to both, maybe? Nice. Flexible mathematicians. Or swap x's and y's and solve for y if possible. So, and solve for y again if possible. Step 3. If using the first option, right, where you've solved for x in terms of y, then you have to add the step of to express f inverse as a function of x, you have to interchange x and y. Or, right,
once you've solved for y, right, your equation is already in y in terms of x, right? Or the equation is already written as y in terms of x. Right, so there's nothing that you really need to do. And the resulting equation is y equals f inverse of x. Example 4, if we have to find the inverse of f of x equals x to the power of 3 plus 2, we've got two options. They're going to do the same thing though. Right? I'm used to just switching the x's and y's and solving for y again, right? Or if you prefer the first option, right, I'll do this. Show both ways and show you that they're the exact same. Right? So your first option is, well, either way, we're going to write y equals x to the power of 3 plus 2. The first option says, okay, well, now instead of solving for y, right, solve for x here. And so you're going to get x in terms of y. And so, well, solving for x, right, we get y minus 2 is x to the power of 3. Slowly shaking out the x, right, we take the third root of y minus 2. But for me, my little personal hang up, right, I like to have x on the left-hand side. So in that move, I'm also going to put x on the left-hand side. So I do x is the third root of y minus 2. Now I've got x is the third root of y minus 2, but now because I still want to have in terms of x, right, the inverse is in terms of x, I still have to swap those x's and y's, right? And so I have y is the third root of, x minus 2, right, swapping those. So I land at f inverse, oops, make a nicer inverse. F inverse of x is the third root of x minus 2. Or the second option, either one that you prefer, it's fine by me. I still usually write y equals x to the power of 3 plus 2, right? I write it, replace the f of x with a y, but then now I'm going to swap wherever I see an x, I'm going to put a y, and wherever I see a y, I'm going to put an x, right? And so now I've got x is y to the power of 3 plus 2. Now solving for y, right, that's going to get me my inverse function. And so same deal here, x minus 2 is y to the power of 3. y is the third root of x minus 2. So f inverse of x is the third root of x minus 2. Roughly the same amount of work. I guess I made the second option look a little bit better because I put a space. Here's an empty space line on the first option. But same amount of work, it's just whichever you prefer. All right. Just as a rule, and we're not going to get into the graphing and the reflecting and the shifting and all that fun stuff unless we absolutely need it later. But just so you know, right, the inverse of a graph, we get it by reflecting across the line y equals x, right, which is this diagonal line. And so I guess I should show, here's the end of my example. And the graph of f inverse is obtained by reflecting the graph of f about the line y equals x. So for next day, right, we're going to finish 1.5. So we'll start with logarithmic functions. So next day, we're going to finish 1.5. Right, so if you've already read it, then that's great. We'll continue on logarithmic functions. But also, if you haven't, read section 2.1, which is where we get into tangent lines, right? And so we'll finish chapter 1 next day, but I think you guys did great for coming, paying attention this whole time. Anyways, any questions? So labs start this week. So if you had one yesterday and you missed it, you might want to catch a different one. But other than that, I know nothing about the labs. Well, I do actually. See you guys on Thursday. See ya.